morning, everyone. And thank you for joining us today for the Innovation in Heat Pump-Based Heating and Cooling webinar. This is our 15th webinar so far, and the last one this year. I'm Savina Cenuse. I'm Senior Communication Manager at EHPA, and I'm happy to welcome all of you today. Innovation in heat pumps is the topic of the day. It happens more invisible than visible, but nonetheless, it drives the industry forward. Today, we'll present innovations that we believe will open new application areas for the heat pump technology. We will talk about oil-free compressors and their advantages. In it, we plan to cover the inherent technology advantages of oil-free compressors, which have enabled them to become the high-performance standard in the commercial chiller market. Then getting into why these same benefits are critical to the heat pump market and what specific applications have the best opportunity to realize these benefits today. Also touching on the additional component innovations Danfoss has created to complement these compressors in a high performance and reliable heat pump application. We will move to a new generation of heat pumps using a low GWP refrigerant. This is a reaction to the F-gas regulation and is a step many manufacturers are taking. We will learn from CHEMOURS and Stiebel-Eltron how they cooperated to make a new heat pump that is future ready for the next 10 years. We will end on a very positive note. The world of new technologies is developing faster than anything else. Today is the talk of the town in a crisis that requires a reliable cold chain at minus 80% degrees for the storage and transport of vaccines. As you can imagine, a very helpful product to remedy the COVID-19 pandemic. We will find out more about the technologies that can be used in cryotherapy and ULT storage applications, as well as about their usability as a source of heating from Mirai Intex. Happy to welcome everybody, and let me introduce our speakers today. Drew Turner is currently Global Marketing Manager for Danfoss Oil-Free Solutions. He has been in the HVAC industry for 23 years, and with Danfoss for the last 6 years, holding a variety of roles over the career, including product support, marketing, planning, business development, market research, in addition to the current position. He is a contributing member of several industry committees and has published a few papers and trade journal articles. He holds a bachelor's in industrial engineering from Oklahoma State and a master's in business administration from the University of Colorado. Welcome, Drew, and thank you for the effort of waking up so early today.
No, thank you for the opportunity, Savina. Yeah, good, very early morning from Colorado, everybody.
Yeah, I can understand. Drew, just a second, because I would like to first introduce all the speakers, and then I'm gonna give you the floor, okay?
Okay.
Thank you. Okay, so we have also Johannes Brugmann. He's the head of R&D heat pumps at Stiebel-Eltron. Dr. Johannes Brugmann studied energy and process engineering at the University of Essen and received his doctor's degree in the domain of photovoltaic simulations with the title Planning of Photovoltaic Facilities with Storage and Additional Systems Concerning Energetical, Ecological, Economical Aspects. He joined Emerson in 1999 as Director Customer Service Strategy. He joined Stiebel-Eltron in 2002 as the Head of Planning Department of Heat Pumps. In 2007, Johannes has become the Head of Product Development and Production of Heat Pumps and Air Ventilation Systems. In addition to that, Dr. Brugmann is a member of VDI 4650, Chair of Heat Pump CHEMOURS scheme, and he belongs to the board of EHPA. Welcome, Johannes. We continue with Loic Chereau, Heat Pump and AC Business Development Lead, low GWP refrigerants at CHEMOURS. Loic has over 20 years of experience in the chemical industry, including at DuPont, Arkema, Dow Chemical, with various roles in commercial and technology. More recently, he developed a good understanding of how low WP refrigerants are being adopted within the AC and heat pumps industries. Considering the performance and redesign envelope perspective as an alternative of HFCs. Good to have you here, Loic. Vladyslav Tsyplakov, Business Development Director at Mirai Intex. The company manufactures turbo compression equipment and air cycle refrigeration machines. His responsibilities include market development, sales oversight, and strategic operation management. Vladyslav has been with the company for over 5 years and is spearheading the transition to natural refrigerants in the ultra-low temperature market. In addition, Vladyslav is a member of the Cryobiology Commission at the International Institute of Refrigeration. Thank you for joining, Vladyslav. I now invite you to listen to our speakers' presentations. We will start with Drew, who will talk about Danfoss oil-free technologies for water and to-water heat pumps.
Thanks, Savina. Can you see my screen?
Yes, perfectly.
Okay, excellent. All right, thanks and welcome everybody. And once again, good very early morning from Colorado. So as Savina mentioned, I will be talking about Danfoss oil-free technologies and specifically for water-to-water heat pumps as a part of this innovation session in heat pump technologies. And trying to advance the screen, give me just a second. It's not advancing. I'm gonna try to reshare, hang on. Okay, can you see it again?
Yes.
Okay. All right, so when you start talking about, so I come from Danfoss Turbocore. So Danfoss Oil-Free Solutions is basically a spinoff of Danfoss Turbocore. And Turbocore has been around for many years now, about 25 years. But when you start any conversation about the technology, it's best to start with the background of it, how it came about. And because of the time limit today, I'm gonna go through this very quick. But it started with the invention from a service tech in Australia roughly 25 years ago of a compression technology that was solving an issue with existing compressors, dynamic compression technologies that were in the field. And when you talk about dynamic compression, that's as opposed to positive displacement compression, which is a majority of the other technologies that are out there. But under dynamic compression, you have centrifugal compression and mainly other is axial. But with that technology, it's very different from positive displacement in that you're throwing the refrigerant instead of squeezing it. And with the throwing of the refrigerant, that's increasing the dynamic, or excuse me, increasing the kinetic energy as opposed to increasing the potential. So it's a very different technology, but that was utilized to drive it to be an oil-free compressor. That was the #1 issue that he saw that he was trying to solve with the new compression technology, is eliminating the oil in the system. And that's on the front end of the compressor, the compression process itself. You also have to solve that same issue on the back end of the compressor. And Vladyslav is going to be talking about this later as well. But how you do that is with different technologies. And Thomas touched on this ahead of the presentation, but there's other technologies that you can utilize for it. But the one that we started with, or the one that he started with, was magnetic bearings, which was being experimented with in the oil and gas industry at the time, 25 years ago when this was invented. But that allowed, so the combination of centrifugal or dynamic compression, along with the magnetic bearings, enabled going oil-free, which was the #1 issue that he was trying to solve at that time. But what that created was and this is the primary driver that you see on the top left-hand side, is the main benefit of reducing the complexity. But it's not just reducing the complexity, it's reducing the complexity and everything that comes with it, primarily maintenance and reliability issues. So if you go from this a very complicated system to a much more simplified system, then you eliminate a significant portion of the issues that you face with HVAC systems out there today. But the other thing that the technology drove, so the other goal, one of the main other goals, of course, that came along with the invention of this compressor was to also significantly improve the efficiency versus what was out there at the time. And part of getting there was the centrifugal compression, both the centrifugal compression itself as well as the 2 stages of it that's built into this design. And then the permanent magnet motor, which also improved the efficiency, along with what I haven't mentioned already is the integrated variable speed drive. So every turbocore compressor has an integrated variable speed drive into it. But what that means in the result in terms of efficiency is roughly a 40% improvement over the technology that's out there today. And that's versus HFC constant speed screws. The other thing that it drives, and this was a part of the goal, but it's really a byproduct of the technology solutions that gives oil-free, that enables oil-free, is that if you have centrifugal or dynamic compression and magnetic bearings, those 2 portions of the front end and the back end of the compressor are the main noise generators. If you eliminate those, then you eliminate all the noise that comes from those because you have no metal-to-metal contact. And so the result is something that is significantly quieter than everything that's else that's out there today. So if you have no contact, you just primarily have the noise of the refrigerant going through the compression process. And so that ends up meaning about 8 dB quieter than an equivalent capacity screw compressor. If you know noise, that's a logarithmic scale. And so every 3 dB reduction is about a 50% reduction. So it's significantly quieter and significantly less maintenance. So this one, the reduced complexity, is the main driver for that. If you have no oil system to maintain, then you have no maintenance of that system. The other benefit that came from this that he didn't really recognize even was an issue at the time, but has become recognized as a significant issue today because of the tracking and the instrumentation and tracking of all the existing HVAC systems that are out there today, is that performance degrades over time. And the 2 main drivers of that performance degradation are the same ones that I was talking about that drove the noise levels. So if you listen to a screw compressor about 5 years after it's installed, it's quieter. And the reason for that is because that metal-to-metal contact is worn down. And what that is loss. So it becomes quieter but it also drives losses. So if you decrease that metal-to-metal contact or wear down that metal-to-metal contact over time, what happens is that you drive losses from the high side to the low side. And so with no contact and with no oil in the system, which is the other main factor driving performance degradation, if you eliminate both of those, then you should have no performance degradation over time. But that only matters if we can prove it with our own technology, that it doesn't degrade on performance over time. And so that's what we've been working on doing, is testing out our compressors in the factory 10 years or 11 years after they were first installed, because they're also tested when they go out. Ultimately, we want to get to a sample size, something more like, for the other Six Sigma nerds, about a 32 sample, so that we can get that normal distribution. But at this point, we have 2. And we just tested 2 more, but we'll get the report on those soon. But the result was about 0.4%, 0.5% performance degradation over 10 years, basically proving the hypothesis. And with refrigerants, the point that we make is, as you go, and this ties back to the dynamic compression, as you go low GWP and as you minimize flammability with the move to low GWP, that in turn pushes you down the density line. And to be able to get to the minimized global warming potential, and I'm sure Loic is going to talk about this as well, but to get to the minimized GWP level, but at the same time, minimize the flammability risk associated with that. That in turn drives you to technology that is going to be optimized for moving a high volume of lower pressure refrigerant, as opposed to a lower volume, squeezing a lower volume of high pressure refrigerant. And that in turn, of course, drives you towards dynamic compression. So it all ties back together. The other point that we like to make is that turbocore is not new. So I already kind of touched on this, talking about the history, but the first compressor was invented in 1995, first commercialized in 2001, and a full portfolio has been developed over those 25 years, or roughly 20 years since that first commercialization. That includes now, and this is where we get into the heat pump critical factors. When you look into a heat pump application, especially a larger industrial or commercial heat pump application, usually it's a combination of lift or differential temperature and pressure that needs to be done to have an optimized solution for it. And what that 25 years of evolution of the compressor portfolio has driven is that broad portfolio of optimized solutions. And whereas we have compressors that are optimized for water-cooled chiller applications, more of a hybrid design for air-cooled chiller applications, as well as others. And then the most recent design that I'm going to talk about a little more detail on next, for water-to-water heat pumps, it's actually a combination, especially of these two, the medium and the high, that drives the most efficient solution for a specific application, especially a large water-to-water heat pump. And that's what I'm going to talk about a little more on. But this is the compressor. And with the compressor, it's important to also talk about the forces that you're managing. So the high lift compressor, what you're trying to manage is higher forces for the heat pump applications. And with those higher differential temperatures and pressures, managing those forces is a little more complicated with the magnetic bearing design where you have no contact. So again, it all ties together, and coming back to that. And so what you can do though to help balance those forces is change the mechanical design. And so what we did is we took that second stage of compression, moved it down to the opposite end of the compressor so that those axial forces on those bearings are pulling back against each other, which help enable that capability. And this illustrates that. So this is that new latest design. And what that enables is, if you're we're talking about heat pumps today, but if you're doing an air-cooled chiller in Dubai, we can do that now. We didn't used to have that capability. But what we're especially focused on is these water-to-water heat pumps. And there's several reasons for that, but I'll talk a little bit more about the detail on that. But tied to the trend to heat pumps, as I'm sure you heard about last week and several other times as a part of these EHPA webinars, is the need for thermal storage, both cooling storage as well as heating storage. It's the same ultimate driver of integrating in more renewables that drives the need for this as well. And we now have that capability. But what we're specifically focused on is especially the district heating market and water-to-water heat pump applications. As I mentioned, there's several reasons for that. But the optimized technology, the technology is optimized for that. And if you focus on district energy especially, and you focus on water-to-water heat pumps, that in turn drives you. If you're going to focus on the more distributed, I've seen a lot of publications about the move from centralized to distributed heat pumps as a part of these district energy systems. And the reason for that is because as you move out in the grid away from a central generation plant to more the distributed, you also move up in general in the heat recovery temperature because you're recovering the heat off those symbiosis applications where you're providing both the cooling and the heating. That in turn means a more efficient heat pump. And that is where our technology, as shown here with the optimization of the different compressor designs to the different operating temperatures and differentials that you do as a part of them, gives you the most efficient solution. And that in turn drives also the symbiosis benefits of being able to benefit or get a dual revenue path from both the cooling as well as the heating efficiency and performance and delivery of those. And this just highlights for a specific application, those combination of operating temperatures that you're going to operate at for the application. So for a water-to-water heat pump, for a specific operating heat recovery temperature, and it's kind of hidden behind here right now, but it's at about 15 degrees Celsius on the coming into the evaporator or heat recovery temperature, and 69 degrees Celsius on the discharge coming from the compressor, which is up at the upper end of our capability. But as you get into a more air-to-water heat pump application, you push down this line. So our technology is also optimized today, even with the higher lift capability, it's optimized for the water-to-water heat pumps, and it would be trading off capability for the air-to-water heat pumps. So it's best with the technology, with the expanded capability of this technology, to focus on water-to-water heat pumps. And finally, I know I'm over on time, Savina, I apologize. I just want to highlight as well, we have a very broad and expanding portfolio of components within the Danfoss portfolio, specifically optimized and tested. Those are the two key things to remember. Not all oil-free components are the same, but if you look at the Danfoss portfolio, all of those components that you see are optimized and tested to the specific application they're going to be used in. So for this water-to-water heat pump application, where we can provide 50 to 70% the component value of it, we have that optimization in that broad and expanding portfolio. And that's it.
Thank you, Drew. Actually, you're right on time, so that's that's great.
Fantastic.
It was very interesting, especially for also for someone like me, who's not a technical person, to listen to your presentation. And also, what I really liked is the fact that you started your presentation with the background for innovation and how important this is, and also to see how long it takes actually from that innovation, from bringing the product to market to actually developing that product portfolio. So you said 25 years, and it made me think about this, I'm not sure exactly who said this, building on the shoulder, building things on the shoulder of giants or something like this. So very, very nice. True. Yeah. So you talked about higher temperatures versus low temperatures. How is this applicable, this innovation applicable, especially in water-to-water heat pumps? You talked about optimizing heat pump applications, the symbiosis applications, and bringing the benefits of oil-free compressors to heat pumps. My first question to you would be, since you introduced these oil-free compressors to the market, fairs and exhibitions are missing. How did you reach your customers?
Yeah, that's a very good question. A lot's changing in that area right now. What we've started to do, so we rely on our OEMs, or our original equipment manufacturers, mainly to get word out on this technology. But as we broaden the portfolio to get into district heating applications, especially, we also benefit from the fact that Danfoss has a broad portfolio of district heating system components and those customer relationships as well. So we've leveraged those existing relationships as well to help drive getting the word out on this technology and the presence of this technology in the district energy market as well. So it's a combination, right? And doing webinars such as this is a perfect example, but it's beneficial when you have a company that has an extremely broad portfolio of components for any application. And that includes district heating, and that's what we've leveraged here as well. Thank you.
From a technical perspective, which share of the market do you think can make use of oil-free compressors? I know that you touched upon this in your presentation, but can you elaborate on that a bit?
Yeah, absolutely. Ultimately, we see that, especially for those larger industrial and district energy applications, where from the start, they're going to be very focused on the long-term performance of this technology. As their life cycle cost models build in the long-term performance and that factor of the equipment, along with the efficiency of the equipment at the design point, as long as that life cycle cost model is expanded to include that factor, we say that the larger market is going to integrate this technology as well as it has in the cooling market as well. In fact, the driver in the heating market, especially in the industrial and district energy market, is at least as much there on long-term performance. And so ultimately we see that it will, whether it's our technology or an equivalent by competition, that it should take about the same as it has in the commercial cooling market. And that's around 30% market share of the total market.
Thanks. And I have also a question for you. Thomas shared about a discussion that he had on high temperature heat pumps. And an expert said that the temperature range above 200 degrees Celsius is not available to ordinary heat pumps. Not so much because of the refrigerant and components, but because of the oil quality that is not suitable to these high temperatures. Would oil-free compressors help?
Theoretically, yes, but you're going to trade off the ability to balance the forces, right? So absolutely, oil, we absolutely see it as an opportunity, and especially in heat pump applications, because if you're not going to break down oil as a result of operating at higher temperatures, then you theoretically should have an advantage. But you have to be able to go oil free, you have to have no contact. And if you have no contact, then you have a much harder time to balance those increasing forces that you go as you get into that higher temperature, above 100 degrees Celsius up to that 200 degrees Celsius range that you mentioned. So it's a very different technology. Well, it's possible with the technology, it's just a significant modification of the technology to enable it. And as I mentioned in the presentation, we have about 69 C limitation today. So we got a long way to go to get to 200.
Thanks. And a last question for you from our colleague, Dan. What kind of permanent magnets does the compressor use? Have they gotten better and cheaper now than the EV market is making so much progress in that field?
Yeah, so there's a long answer to that, and I know I can't give a long answer. So the combination of, so all of our compressors use a combination of permanent magnets and trim magnets, right? The trim magnets are what maintain the operation with the changes, with the variables of the operating temperatures and pressures. So that's the first part of the question. The second part of the question is, have they gotten cheaper? No, the permanent magnets themselves and the rare earth elements that are built into those have not gotten cheaper, but you can improve the cost position of those by changing the designs of them and evolving the designs of them. And so we have been working on that and improving the cost position of the resulting compressors as well. So that has changed. But yeah, the base technology, there's not much you can do to change that.
Thanks a lot, Drew. Okay, we continue with Johannes Brugmann, who will present next. His presentation is about R454C heat pumps with high efficiency performance and excellent operating limits.
Good morning. I hope you can see my screen and can hear me.
Perfectly.
We decided in 2016 to start a new development, and one of the main goals was the development of the heat pump with a new refrigerant that is in line with the objectives of the F-gas directive and can be used also after 2030. For that reason, we investigated, of course, the probably refrigerants that can be used, and you can see the old refrigerants that are, or the common refrigerants that are used today, and we looked to the refrigerants that are below R32, because that is one of the refrigerants that is below 750, that is mentioned in the F-gas directive. And we saw, of course, these refrigerants, water can't be used below 0 degrees because then it's freezing. Ammonia is the A3 refrigerant. It's quite not that good. CO2 have a quite poor efficiency, especially if you use it for underfloor heating. Propane, it's from the thermodynamical part a very high efficient refrigerant, but flammable and explosive. Then we have investigated R1234 YF. That is pretty good also for the condition, but the efficiency and the volumetric cooling capacity is very low, so you will get high units. Then we have these HFOs. There is R454C and R455A. It's not written here, but it's also one of these refrigerants below 150 and with very high efficiencies. And it's an A2L, so it might be flammable. And the main reason, the beauty of these refrigerants, that they are below 150 in the GWP. Then we have the other HFOs. It's R410A, which so it's comparable to R410A from the efficiency and capacity, and it's have usually a GWP of 400 to 600. And then we have R32 as a big part of R410A. And we investigate all these units. And one of the key factors of this investigation was that we used in parallel a simulation tool to avoid big measurement programs. And our decision went to R454C, and I will show you the results that we achieved with this refrigerant. The result was an air-to-water heat pump for residential heating with 5 and 7 kilowatt at A-7. And we reached with this refrigerant R54C and usual components, the COP of 4.3 up and 4.6, depending on if we calculate the defrost cycle or not. So, for example, the WPL7 has to use the defrost cycle because it's the defrost mode came into the time frame, and the WPL05 doesn't have a defrost cycle because concerning to the EN 14511 wasn't necessary, and you can see roughly the difference between with or without defrost cycle in the COP. Then we achieved a minimum outside temperature of -25 degrees, so we can use these units also in colder climates, and the beauty of this are the limit of the flow temperature. The maximum flow temperature is 75 degrees, so we have we can use these units in applications of old buildings, and we can ensure a hygienic hot water supply without any problem. So to reach 60 degrees in the tap water tank is no problem. But R444C have also some disadvantages. One of these disadvantages is quite high temperature rise of 6 to 12 Kelvin, depending where you are in the wet steam area. And you can see it in this slide that the temperature decreased from the wet to the vapor side. You have also the possibility to use this light effect if you have a recuperator, for example, and that's not new, that's quite old common technique for R45 or R407C that was used or is used today with a GWP of around 1,700. And if you use this temperature glide, you can also increase the efficiency. But we had some problems with this recuperator, and I will show it here. In the lab, we measured roughly 0.8 COP points less than we simulated before. And the reason that we lost this efficiency was that the superheat that is heat exchange from the subcooling to the superheat was not completely in the recuperator. And what you can see here is that you can increase the efficiency of the unit from 3.8, for example, to more than 4.8 at these special conditions. If you move the evaporation for the superheat into the recuperator, and if you doesn't, you lose this efficiency, and that is the most important point if you want to use R4C as a refrigerant. So, but last but not least, we developed on top to the air-to-water unit a range of brine-to-water heat pumps from 4 to 15 kilowatts, also with R4C as a refrigerant, and reach also these high temperatures and very good efficiency. Thank you very much for your attention. If you want to have more information, you can find it on our website. Thank you very much.
Thank you, Johannes. I would like to continue because it's the same topic, but from CHEMOURS perspective, considering the collaboration that your two companies had. And Loic will discuss about R454C and R454B, low GWP HFO refrigerant solutions for sustainable, energy efficient and safe heat pump applications.
Thank you, Savina. I'm going to start actually to talk about the F-gas regulation, because this is really the foundation of the work that we in CHEMOURS are doing, but also the work that Johannes at Stiebel-Eltron, but also the heat pump manufacturers are somehow very much aware of and are building on their innovation and their developmental works. The reason I'm really speaking about the F-gas regulation is because of, let's say, the mechanism which is now being in place, to reduce the quota of CO2 emissions. This CO2 quota is really being built on the Montreal Protocol and the Kigali Amendment to reduce, let's say, the CO2 emissions from a refrigerant perspective. Coming from the 410A refrigerant or from the 407C refrigerant, which is also used in the heat pump industry, as you can see, there is a step down on the CO2 quota, which is somehow, permitted, by the current F-gas regulation in Europe. Different than in the commercial refrigeration industry, where there is already, also some bans on new equipment, to use a very high GWP refrigerant like the 404 refrigerant. In the heat pump industry, there is no ban yet, but still anyway, following the same step down we are having on the CO2 quota to reduce the average GWP of the refrigerant that can be used in the heat pump industry. As you can see, there are different choices when you look at, the refrigerant we have from a GWP perspective on, let's say, the applicable solution that can be seen along the years and let's say down to 2030 and beyond. Within our portfolio in CHEMOURS, we have, let's say, two products that we are now more and more, talking about with regard to new developments, which are the 454B and the 454C, which are the Opteon XL41 and XL20, for which, as you can see here, I would say GWP slightly, I would say, slightly higher than 450 for the 454B and lower and below the 150 GWP for the 454C, which is a product that has been adopted by Stiebel-Eltron for their new heat pump. Reason why is, as you can see here, let's say when you look at, I would say the 454C, the GWP, that is featured, by this blend of HFO is really, I would say, a long-term solution when you look at, that phase down. The reason also there is so much also emphasis, on developing a new heat pump with these HFO blends is because of the other alternatives that are today being used by the industry, which is very, I would say, which is very clear, today adopting the R32 refrigerant from different suppliers. But the reason also why the R32 is somehow already now looked at as an interim solution is because when you look at the, I would say, the years along that phase down, you can immediately see that just after 2026, so about 2 years from today, the average GWP will be even below the R32 GWP, which is 675. And this is why we are very much looking at, as an industry and as, I would say, an enabler to bring refrigerant that can be used even beyond that date and really to be used for the next decade. I've been talking a lot about the, I would say, the blends of HFO, and just to make sure, that everyone understands, all these blends, XL41, XL20, so the 454B, 454C, are based on probably very famous refrigerant that you all know, which is the 1234YF, which has been designed mostly, for the mobile air conditioning that is used in any light vehicles. And from that, and that took us more than 10 years, to develop that refrigerant, we have been developing different blends to adapt, the capacity of this refrigerant for different type of sectors and industries. Why now, I would say these two products are being positioned, it's mostly also because of the performance, they can bring into the heat pump. And let's say if the 410A refrigerant is being used, as a reference, the near drop-in solution that can be really considered, as a good candidate to achieve, I would say, the higher efficiency from the 410A refrigerant is the 454B. And this is really, I would say, the near drop-in refrigerant, that can be seen coming from the 410A. If let's say the 407C would be the reference, the immediate near drop-in solution, that could be also considered is the 454C, because of, again, the performance, that can be achieved, even though there will be always a redesign to be taken into the heat pump to make sure, the efficiency, can be as good as it was from the initial HFC refrigerant. Now, there is also a good thing, when we talk about the 454C refrigerant with regard to the temperature discharge, because if, for instance, this product is being considered and adopted from a 410A refrigerant system, there will be a much lower temperature discharge. That is also interesting, in some cases, to increase, the I would say the lifetime that you can expect, because you are in a much less stringent envelope of use for the compressors. And this is why also this product, can be of interest, coming from the 410A refrigerant HFC, but of course also having to redesign the equipment. The last thing here I wanted to talk about, because this is somehow the trigger for developing and for using these two blends, is the flammability and the behavior these products are having compared to the HFC 410A or 407C that are A1, that are non-flammable. These two products, these two blends, are mainly flammable, so which means that there are some risk assessment to be considered when the OEMs are using these refrigerants. So there are different factors and means to mitigate then the risk, depending on, again, the refrigerant that is used, to make sure that they are applicable. There is, of course, some differences also being used in a direct expansion system or an indirect expansion systems. And let's say, for instance, for for an indirect expansion systems, like chillers, if they are used outdoor, there is no mitigation that is needed, and there is no limitation in terms of charge size that can be used for these refrigerants. So there are different standards to comply with when we look at A1, A12, and of course A3 flammables. This is something that we have tried to also ease and facilitate within the industry, with a charge size calculator, because there are different conditions, conditions and standards that needs to be followed, by the OEMs, to make sure these I would say OEMs can use in a correct way the refrigerants, depending on the charge size, of course, the location where the heat pump will be used, be it for instance used and installed on the floor, on ceiling, on the wall, but also different type of, let's say, room. So the dimensions of the room is also something to consider, to make sure all these equipments will comply with the EN standard, be it the 378, but also the 2-40 EN 60335, which is applicable for the heat pumps and for the appliances. Again, I'm talking about these safety standards, because when we talk about refrigerant, there are different type of flammability behavior and classification of these refrigerant, be it an A2L, like the HFO blends we are developing, but also now, as we see more and more also, at least discussion about the use of flammables like the propane A3 refrigerant. There are still today very strong limitation on the charge size, which is 150 grams for such flammable products. And because of that, there are clearly some restrictions and limitation where propane can be used in terms of, let's say, charge size, and therefore, the heating capacity that can be achieved for such heat pumps. Last but not least, of course, the national and regional building codes, prevails, and making sure, be it in Europe or in the US or elsewhere, these, I would say, these standards and codes need to be also respected. Moving on and gearing up more on, let's say, the difference between the A2L and the S3 refrigerant, mostly propane, because this is one of the very popular refrigerant which is being developed today also on new equipments. The reason why the industry is still very much and greatly considering the A2L refrigerant is because of the lower and much lower flammability risk there is using an A2L refrigerant. When you look at the say this risk of flammability, you very much could continue that in volume, you would require at least about 4 times volumes of, sorry, there is about 4 times of refrigerant A2L that is equivalent to the flammability that is achieved by an A3. So this is the reason. This is mostly driven by the LFL, the lower lower flammability limit of the refrigerant that needs to be I would say looked at here. With an A2L, there is about 5 times lower combustion energy compared with an A3, and this is why again an A2L is much lower in terms of risk, in terms of flammability when you look at this type of HFO blends. Now, I would say as a conclusion and quick conclusion, of course, you can probably see here, on the right hand side, differences of A2L refrigerants, so the 452B and the 290, so the propane, and as a flame say propagation, it's clearly seen and featured by the industry that propane, so flammable refrigerant, and A2L refrigerant are really on 2 different markets for different reasons, but mostly because of the current limitation there is on the charge size, and therefore on, let's say, the heating capacity that can be achieved by the current charge size limit which is on the A3. And beyond that, it's also I would say thing that not only on the heating capacity limit that there is pretty much seen and achievable with an A3, these systems are also I would say developed for being used either outdoor and indoor, and there is much more proportion of using an A2L refrigerant when we consider a heat pump to be used indoor. Very quick on that, because it's been also presented by Stiebel, but not only Stiebel, there is more and more adoption of our HFO blends, the 454B, the 454C, be it for chillers or large heat pumps. And this is, I would say, the clear trend we are seeing to go to a lower GWP HFO. And of course, there are also other let's say refrigerant and systems that can be considered, but on the long term, there is a clear trend, to see more and more, lower GWP solutions, be it again, I would say our blends, but also other systems. As a conclusion, and as I said earlier, there are different factors to consider our products, our A2L, be it the refrigerant that is used as an incumbent, so be it the 410A or the 407C, and from that we can already drive probably the selections, but there is also I would say some clear element that now we are continuing to learn, which is also the need to redesign the equipment and to really, I would say, start from the beginning, ideally, with the OEM to make sure, all these, I would say, factors that are being put now in place, with an A2L, and especially on risk assessment, is well considered and understood by the manufacturers.
Thank you, Loic. I would like to continue with some questions for both of you, Johannes and yourself. Maybe Johannes wants to answer this first question. Do you think that the new refrigerants are suitable for all heat pumps in the residential range?
Yes, I think so. We can achieve temperatures up to 75 degrees, and I guess that's enough for all renovation buildings and also existing buildings without renovation. And for that reason, I'm pretty sure that it's enough. commercial appliances, it could work if you need the 60 degree in a hot water production, and so I guess that it's applicable for all these kinds of applications.
Thank you. Loic, do you want to add to that?
Not so much, because I think what Johannes said is very true.
Okay. Then let me ask you something else. Some manufacturers have already announced that the current mid-range GWP solution will find an end towards the end of this decade. Do you agree with that? And what will come next?
I would agree, of course, and this is of course, also I would say the essence of our work here to develop lower GWP than the current, one which is I would say largely been adopted and used by the new heat pumps, which is the R32. So as you can see, this
Johannes, maybe you want to, because I think there's something going on with Loic's internet connection, unfortunately. So
yeah, I can try. So
yes.
What he's showing is that R442C, for example, is far below the requirements of the F gases in average, but of course we will use more R444C or refrigerants for heat pumps in the future, because the number of heat pumps in Europe will increase. But nevertheless, there are a lot of other units that can be replaced. For example, today R410A that has a GWP that is roughly 50 times higher than the R454C, and we see two points. The one point is that they could be maybe a border of 150 in the future in the F-gas directive later on, maybe, like this today for other appliances. And the second is, of course, the price of F-gases will increase, like it was 3 years ago, where the prices exploded roughly 10 times. And we see that also that in the future, these kind of refrigerants with 150 are more expensive than natural refrigerants, of course, but they are acceptable. The beauty is that you have less costs on the safety issue that you have to use, for example, for propane, where you have an explosive refrigerant, and for the comparison, the R454C is less risky than propane.
Thank you very much, Johannes. We will continue with Vladyslav now. Let's hear from you, Vladyslav, about simultaneous ULT cooling and heating with air cycle principles and practical applications.
Thank you, Savina. Thank you, everybody. I will start with presenting our company. At Mirai Intex, we are an engineering company, and we are dedicated to the protection of the environment through the implementation of innovative technologies. Mainly, we specialize in the design and manufacture of turbo compression equipment, and based on which we produce the safest and cheapest to operate ultra-low temperature solutions. Our company was founded in 2015 in Switzerland, and currently we operate from an office in Vienna in Austria and a manufacturing facility in Brno in Czech Republic. So coming down to the background of the air cycle technology, the first machine was developed in 1851 by John Gorey for ice production, and looked something like this. Of course, this is a replica, not the original model. But then it was further developed by Joseph Coleman and Henry and John Bell, and therefore it is commonly known as a Bell-Coleman cycle. So that was done in 1870s. But further, the technology was developed and used on board of ships for food refrigeration. And currently, you can find the technology on high-speed trains or in every aircraft for climatization. And why it is used in aircraft? Because there is no phase change of the refrigerant. Thus, it can work at different altitudes and pressures. So coming down to this refrigeration cycle that we use in our refrigeration machines, here we have a centrifugal compressor sharing a shaft with the centrifugal expander. And between them is the electric motor. Usually the airflow goes something like this. The air is heated in the compressor, cooled in a series of heat exchangers. First, we have the end cooler. We're going to look at this one a little bit closer later. And then we have the recuperative heat exchanger. After that, the air is expanded and the air can become ultra low temperature and can be supplied directly into the chamber or to a heat exchanger, which is located in a chemical process. So after that, the air goes to the recuperator and back to the compressor. More specifically, we have the end cooler here, which can work as a heat pump. So because we have a lot of heat after the compressor, we can supply this heat to either water or air, depending on the machine that we are talking about. So the applications for our refrigeration machines range from storage applications for cryotherapy, biomedical and food storage, and process cooling and freeze drying, as well as climate testing. So the benefits of our systems, number one is the fact that we use air as the refrigerant. You don't need to refill it and it's environmentally friendly. So coming to the ultra low temperatures, if we were talking about a temperature of -80, for example, with air, we're substituting two extremely harmful refrigerants, for example, R404A and R23. R404A has about 4,000 GWP and R23 has around 15,000 GWP. So as you can see, to substitute those huge values with zero is a big feat. So secondly is the safe solution. We don't have any chemically active substances and there is no risk of fire or explosion because we don't use oils in our system. We also have an oilless compressor design, but we use air bearings. So this results in reduced initial and running costs for the machine. So you have less downtime for maintenance, oil refills, oil changes, etc. So due to the lack of contact in pairs, we have the long life cycle of the equipment, and it's easy to service and maintain without any special training. And also with high energy efficiency, we have reduced energy consumption up to 30% by having a shared shaft between compressor and expander, because expander generates the energy, which is fed to the compressor. But also you don't need there's no need for defrost procedures of the chamber, and you can recover the heat from the refrigeration cycle. Operating stability is also an important point, because the machine is continuously operating throughout the whole cycle. There are no peaks on the power grid and on the cooling water. This usually happens in freeze drying cycles when there is a huge cooling demand. You have a peak load on the water circuit. We don't have vibrations and no high noise. This is a feature of centrifugal compressors. There's a low noise feature, and you don't need a separate machine room for the installation of our units. Temperature accuracy of 0.5 degrees is achievable due to a variable speed drive. We can adjust RPM and as a result, adjust the temperature output. And as we all know, legislative compliance is very important. As the amendment to F-gas regulation is coming along, we need to make sure that our technologies, our refrigerants are a long-term future solution. And also the control systems is the fact that you can connect higher level communication protocols to our machines. But coming down to to our products and what type of heating you can get from it, usually from the water-cooled units, you can get the low potential heating. So if, for example, the machines are cooled with the temperature of plus 20 degrees, you can harvest about an additional from 8 to 10 degrees of heat. So the outlet temperature would be between 28 and 30 degrees with the thermal power of 14 to 15 kilowatts. Coming down to the air-cooled machine, if the air temperature outside is +20, we can heat this air up to 70 degrees with the thermal power of 22 to 24 degrees. And we have actually realized a project like this, and I'm going to talk about it a little bit later. So with the following machines, this is our new product that we announced this year. It's still in the body of the smallest machine, but we can harvest thermal power, which otherwise would be just thrown into the water circuit, of up to 24 kilowatts, but low potential. So this is the heat that you can go and put into a heat pump to heat it further. And coming down with bigger machines, we can get 35 kilowatts. And with the biggest machine, which we are going to announce later this year, we can harvest about up to 130 kilowatts of thermal power, but once again, with a low temperature, not higher than 30 degrees. You can cool the machine with 30-degree water, then you would have a 40-degree water outlet, but still it's a low potential heating. So coming down to some reference projects where we have realized these applications. So speaking about the cryotherapy application, we did a chamber for a client in Germany, in Karlsruhe. It's the first whole body cryotherapy chamber using only air as the refrigerant. We use the Mirai Cold 10 open cycle air cooled unit, and there is a double chamber design. You can see here on this picture that there are two chambers. The first pre-chamber is like the drying area. You go there, you stay there for about 1 minute at -60. You let your skin dry, and after you go into the main chamber to -110. You spend there from 2 to 3 minutes, depends on how thick your skin is. But this really helps with recovery from sports and treating some illnesses. So we produce around 4 kilowatts at -110. So we can cool both chambers with one machine by having smart air distribution inside the chamber. But in addition to that, we also collect the heating power of the machine into the main room of the facility. So you can see it here. We have installed a valve here, which we can control either to release this hot air outside or into the premises of the facility. So during winter, we can switch the valve and blow fresh but hot air into the chamber. We believe, not the chamber, I mean the room of the cooling facility, and provide fresh air, hot. And this allows them to really have fresh air, not recirculation air, and keep the windows open and have pretty much a free heating for the room. And this is supplied through a duct like this. So if you move this, it can be used as a drying station. After the shower, after gym, you can come down, dry your hair, dry completely in an instant. And once again, it can provide about 24 kilowatts of thermal power. Yes. So we did another application, but this is for freeze drying, and I want to mention this to you as a reference that can be used for water-cooled systems. Here we have two Mirai Cold 10 units connected to a freeze drying system. So we started cooperation with Hof, Sonder and Langenbau. We developed a new generation of freeze dryers, and they call it the Hof Cryo Blizzard. So this is the company's own freeze dryer from 1998, but they retrofitted it with two Mirai Cold CWT units. This replaces two refrigeration sets, and each with 12 kilograms of R404A. With GWP of almost 4,000, you can do the math, how much more benefit that does to the environment. And this allows to freeze dry batches of up to 40 kilograms for insulin production. So in the next slide, I can show you how, here is the point for the water circuit. And in such a manner, we can extract the positive heat from the refrigeration machines either to the manufacturing facility or to later stages of the water heating circulation. You can have a heat exchanger here with water to water to heat inside the premise or similar to that. Thank you for your attention.
Thanks a lot, Vladyslav. I had to laugh a bit because when you were presenting this chamber that is using the cryotherapy technology and how is this benefiting humans, our health and so on, I was thinking about Wim Hof, who's this Dutch guy who's teaching you how to breathe and then jump into very cold water and the benefits on the health and so on. And your next slide was with this Hof. It was called Hof. So I had to say this. Yeah, as a joke. I want to ask you one question because we don't have a lot of time left, and I also want to give the floor to all the speakers for a final remark. So since your primary market is this ultra low temperature applications, during these times, during this pandemic, your cryotherapy applications are in high demand, right? What are the challenges and the lessons you faced and how you overcame them to address the current market needs?
Well, I wouldn't say it's only the cryotherapy applications. It's mainly our refrigeration machines for the storage of vaccines. So currently there is a high demand for temperatures such as -80. And unfortunately, there aren't many ways to achieve -80. Either you use high GWP refrigerants such as the R23, or you go for the air refrigeration solutions. So this is why we're currently working on a lot of projects to help to solve the crisis and build the logistical chains to supply the population with vaccines.
Thank you. Great. Okay. Thanks to all of you. I want to ask you for a final remark as we are approaching, I mean, it's the end already of the webinar. My question to you, and I would like to do like a tour de table with all our speakers, would be if you had one wish that would speed up the market adoption of heat pumps, what would that be? Drew, Johannes, Drew, maybe to start to finish as we started in the same order.
As far as the market adoption of heat pumps, it's really not. It's not the adoption of heat pumps so much. I would speak to as much as the methodology of the adoption of heat pumps. What we would advocate is that I spoke to the district energy model. The district energy model is absolutely critical to the future adoption, significant growth of heat pump adoption itself, as well as not driving a long-term blowback to that significant growth in the adoption of heat pumps. Because of the what we would call the grid interactive, reliable adoption of heat pumps and the issues that you can drive if you don't do it in the district energy model. So with the district energy model, there's a much more flexibility with the heat pump adoption to make sure that it's done in a reliable manner with the periodic unavailability of the renewables that are driving the growth of the heat pump adoption itself. So what we would advocate is that's the number one thing that needs to be done is a growth in the district energy model adoption of heat pumps, in addition to the growth of the heat pump adoption itself.
Thank you, Drew. Johannes.
Yeah, what we see today is a big change in the market. So I think heat pumps become the number one in the European heat generator market. we see that, for example, from the Green Deal. You see it in Germany, in the legislation, in the subsidies structure that is generated for heat pump. And from my point of view, now we have the change from gas and oil to heat pumps. And there's a lot to do for the industry to find solutions, not only for the residential, also for other applications, as Drew showed us today. And I guess there are many questions that we have to answer. One is the refrigerant, one are the temperature levels, and the third is that we have also to look a little bit deeper into the systems, that we have perfect system of heat pumps, refrigerant, and also application, and that makes our work leaner. Thank you.
Thank you. Loic?
Yes, I will build on what Johannes just said, because first of all, I truly believe, the current incentives, that are being put in place, by the European member states, is really helping us, the heat pump adoption, speaking about the residential heat pumps. And I think, these regulations, these incentives, are working pretty well. Again, in the residential business, the fact is that there is probably still some work to continue and to make sure there is also much more awareness down in the value chain, at the builders and installers, that the heat pump are not only the small AC systems that have been on the market now for many years as small AC units, but can really truly do more, like an air to water heat pump can bring, not only on the space heating, but also having the sanitary hot water connected on it. So there are a lot of features that a heat pump can make from the recent development that were and are not yet so much clear at the end user. So this is really an element to make sure a heat pump now is not only a small AC unit, but can do much more. And as also the renovation of the building is happening, there it's clear that the adoption of the pump will increase. And probably the best example is that even though, for instance, in the last months, because of the COVID-19 situation, there has been a lot of slowdown into the different industries that the refrigerant are used. But guess what? The pump industry is still on the increase and is still very much busy. Even though the overall economy was down. So which means that these heating systems are really a solution, for the future.
Thank you, Loic. Vladyslav.
I would rephrase the question a little bit, not for the adoption of heat pumps, but for the adoption of environmentally friendly refrigerants. I view the solution quite simply is to tax high GWP refrigerant solutions and subsidize low GWP technologies. As simple as that.
That's great, and I think these are great ending remarks for this webinar, especially during this health crisis, social crisis. Besides the fact that this technology is ready for the market, I think that people are becoming more and more aware of their impact on this environment. They are becoming more and more aware of their own health and well-being. So I would expect that clean technologies will definitely conquer the world finally. So thank you very much for all your contributions, also to this webinar, but also with your work to this market. And thank you for being here, also to everybody who attended the webinar. And I wish you a wonderful day ahead.